Hello, my name is Umer Khatib, and I'm responsible for the primary research and analysis for this project. The amount of urban acoustic disruptions that come from traffic and loud vehicles constitute approximately 80% of urban noise pollution. These noise interferences can contribute to disruption within human and ecological life, as well as wear and tear on mechanical systems. Chronic urban noise pollution exposure is especially prevalent in our home countries in Asia, making this a deeply personal endeavor for our team. Moreover, the lack of priority given to the sound dissipation aspect of current vehicle mufflers is one of the major contributors to this issue. So the primary objective of this project is to engineer, simulate, and revamp a novel vehicle muffler design that not only implements the application of intricate internal geometry, but also addresses the use of materials that are carefully positioned and determined in an optimized manner. This configuration is designed to further improve acoustic performance and ultimately serve as a means of mitigating urban noise pollution.
Hello, my name is Armand Shah, and I manage the simulations and design optimization. The optimization methodology begins by defining a baseline muffler design, model dimensions, and input conditions, then running a simulation to record transmission loss and sound pressure level. Key operating parameters such as inlet pressure amplitude, exhaust gas temperature, inlet flow rate, and frequency range are specified as part of the baseline inputs. Next, a Sobel sensitivity analysis is performed by simulating across parameter ranges to compute first order and total Sobel indices for each parameter. These indices are used to quantify the relative influence of each parameter and identify which ones most strongly affect each performance metric. Finally, the most influential parameters are selected for a target parameter sweep, where bounded variations are tested to determine the geometry and conditions that yield the best performance. The design met the primary theoretical objective of the project by offering an improved means of sound dissipation without compensating direct airflow.
My name is Evan Lee, and I manage the modeling. Our group created a design criteria specifically to prioritize the acoustic metrics within our muffler design. In regard to the scientific principles primarily used to maximize the muffler performance, the group studied a combination of destructive interference, flow acoustic coupling, quarter wave and standing wave attenuation, and viscothermal dissipation. Using COMSOL multiphysics, specifically its material-specific tools, the group experimentally determined material candidates and its positioning within the muffler to improve transmission loss and sound pressure levels. We then explored manipulating the layers of the muffler and using distance between layers as another variable to affect transmission loss.
While the solution fulfilled the project goals and criteria, it is important to note that results are inherently idealized and can therefore not guarantee specific results in real-world context. With current federal deregulation and EPA environmental rollbacks, the reduced incentive for EV production calls for improved traditional muffler technology, such as its theoretical design. Future research would be dedicated towards examining the muffler's performance with thermal degradation and analyzing how the system would operate in a real-world context. Thank you for listening.